Yeah, okay, so I'm going to talk about models of computational effects. And to tell you specifically what I'm going to talk about, I'll start by giving you an example. So here is some kind of computational effects we might like to model. So let's suppose that we have programs which can use a bunch of operations. So in particular, I have an operation called OR, which is binary, so it takes two kind of programs as arguments. And it says non-deterministically choose between the two programs. Then we have another operation called fail, which is nullary non-deterministic choice. And a third operation called cut. So the way to understand these is if I draw a computation as a tree, we can do some kind of depth-first search of the tree and just read off the values that are returned by the computation. But then if we ever see a cut, we just kind of stop and prune everything to the right of the cut. So here we get 11, 12, 13, and then the computation stops. So there is some kind of way of implementing like backtracking computations using these things. I won't talk about this in detail, but just kind of keep this picture in mind. So we want these terms to satisfy some equations. So when we interpret these terms inside some model, we'd like some equations to be validated by that model. So for example, we might like to say that if I do a choice between m and n, where m is a computation that definitely cuts, then this is equivalent to just doing m, right? Because everything to the right of m will just be pruned. Or we can write down some other equations like this one at the bottom of the slide. It's perhaps less obvious why this one is true, but it says under some circumstances we can permute these computations n1 and n2. Okay, so the question I want to ask is how do we actually construct a model of these effects in such a way that we can kind of validate equations like these? Okay, so there is some existing story about kind of constructing models of effects. So the way it goes is we say something like, we can model effects usually using monads, or in fact strong monads, but I'll just kind of forget about strength for this talk. And these, in some way, kind of come from presentations. And here by a presentation, I mean something like a collection of operations together with a collection of axioms, which are like equations we would like the model to validate. And then there's this nice story that says, once we have a presentation, we can actually construct a monad in a canonical way. But then we can actually say more than this, because every operation of the presentation will induce an algebraic operation. And these are kind of the functions we would like in order to actually interpret the operations that cause the effects. So for example, there is some monad that we can use to interpret these computations with cut. So we say something like, a computation is a list of results together with some tag that just says whether the computation cuts. And this actually comes from some presentation. So the presentation just says I have three operations, one called OR, which takes 2 arguments, one called fail, taking 0 arguments, and one called cut, taking 0 arguments. Then there's a bunch of axioms we require these to satisfy. So we say OR is associative, it has fail as the unit, and cut is sort of a left 0. But then the nice thing is, from the presentation, in addition to getting this monad in a canonical way, we also get algebraic operations, which are the things we would actually use to interpret OR and fail and cut. So these are like just families of functions, so OR will just take 2 computations and kind of merge them together in some way by looking at the tags and maybe concatenating some lists. Okay, so now let me go back to these equations. Because if we kind of model effects just using a monad and some algebraic operations, this doesn't really give us a good way of proving that these equations hold. The reason is that these equations have some side conditions that say only consider computations that satisfy some certain property. So only computations that cut, for example. And there's no really good way of expressing these side conditions using this kind of previous story about ordinary monads and algebraic operations. But there is also an existing solution to this, which is to kind of grade the computations in some sense. So I won't actually give you the full definition of graded monad at any point in the talk, but hopefully this will give you enough of an idea of what they are. So we can say something, so here are 2 examples. We can say something like, I have this graded monad, which is graded by natural numbers. So here E is a natural number. And a computation of grade E is a list whose length is exactly E. So lists of length exactly 4, for example, don't form a monad with concatenation, but collectively these lists form what's called a graded monad. A graded monad looks a bit like a monad, except we just kind of assign appropriate grades to the bind operator and to the return. This is, in fact, why I'm asking for an ordered monoid here. The monoid structure gives us the appropriate grades for the bind and return. Or, for example, we could say, we'll grade my list monad by taking lists of length at most E, for example. So there is a graded monad we can use for this cut example. Essentially, the way it works is we just take the ordinary monad I showed a few slides ago and say, impose some side conditions on the computations. So here I have 3 grades. They're called bottom, 1, and top. You can think of them as bottom says the computation will cut. 1 says the computation will either cut or return something. And top says, well, we don't know anything. So we can say, for example, a computation of grade E, where E is bottom, is a list over X together with a tag which actually we require to be cut. So a computation of grade bottom is a computation that actually cuts. So this forms a graded monad. I won't go through the details. It's kind of not so important for this talk. But we get some graded monad which we can use to model these computations that I showed at the beginning. And the reason this is good is because now we can actually, have a way of expressing these side conditions on equations. So if we take this equation that says R of m and n is equal to m, the side condition now says m has grade bottom, right, which means m actually cuts. So in fact, if you kind of calculate for a while, we can interpret these computations using this graded monad, and this equation is actually validated. Okay, so now the question I want to ask is there a story about presentations for graded monads? So now I want some story that says I have some notion of graded presentation, which will consist of some kind of graded operations with some equations. And somehow I want to extract a canonical graded monad together with some algebraic operations, which I can actually use to interpret my effects. And actually, there is an existing notion of graded presentation, which in fact would allow us to present this particular graded monad. The problem is we cannot present these algebraic operations using this existing notion of graded presentation. So if we say we only care about the graded monad, this is fine. But if we really care about the algebraic operations, and we do because we want to interpret programs that involve OR, for example, then we actually can't use this existing notion. Because we do not get the correct algebraic operations. The reason, by the way, is because in the case of OR, we have several arguments which will, in general, have different grades. So here, D1 and D2. And this actually is not permitted in the existing notion of graded presentation. There's some side condition that says all of the arguments have to have the same grade. And we actually can't extract this OR operation by doing this. Okay, so the goal of this is essentially to develop some nice notion of graded presentation. We call them flexibly graded presentations. In such a way that we can actually extract a canonical graded monad together with algebraic operations. And I mean a suitable notion of algebraic operation to interpret effects like this cut example. So we do this by generalizing this existing notion in some way. And then, yeah, we kind of do all the proofs and show that we get a graded monad and so on. Okay, so for the remaining time, I'll kind of go over this in more detail and say what these things look like, how everything works. I'm not going to give the full details of anything because there's not enough time to do this. But I'll start by saying what a flexibly graded presentation is. So a presentation is first a signature, which means a collection of operations. And in this case, every operation has a list of input grades, here D prime, and also some kind of output grade, D. And given such a signature, we can say I can generate terms over this signature by kind of applying operations to other terms. So if we have an operation whose inputs have grade d prime and output has grade d, we can actually apply this operation to terms of grade d1 prime times e to dn prime times e. And then we get something of grade d times e. It's not so obvious why the e is here, but this is kind of necessary in order to get the bind of a graded monad. Okay, then once we have terms, we can ask for a collection of axioms, and an axiom is just a pair of terms. A pair of terms that we would somehow want to be equated once we construct this model. So in the non-determinism example, we can say, well, I have a bunch of operations, in particular, these are operations, which have appropriate grades, and then also a bunch of axioms. I'm not writing down all of them, but there's some associativity and things like this. And in particular, something that says R of x and y is the same as x, whenever x has grade bottom. So whenever x definitely cuts. Okay, so then the rest of the story is essentially we want some nice graded monad with some algebraic operations. The first step to doing this is to first define a notion of algebra. So an algebra here is essentially a space together with interpretations of operations, such that these interpretations satisfy the axioms of the presentation. So the notion of space here is what I'm calling a graded set. This is like a collection of sets, one for every grade. So you'd think of like the set AE as being computations of grade E. Then the interpretations are just a bunch of functions satisfying some properties. And then once we have these, we can kind of lift the interpretations of operations to interpretations of terms, and then ask for for the interpretation of each side of every axiom to be equal. Okay, we can also come up with some notion of equational logic. This essentially just says which equations we can derive from the axioms. So there's a bunch of rules for deriving equations. This on the slide is the rule for applying an axiom. There's also a rule for congruences and some other things. And this equational logic is kind of the appropriate equational logic in the sense that it's actually sound and complete. So an equation is derivable exactly when it's true in every algebra. Okay. So now, actually, we can construct some graded monad. The easiest way to do this is essentially take the terms and quotient by the equational logic. So I'm not writing down the full details of this, but we do get some graded monad, which actually is canonical in some sense. Precisely, it satisfies some universal property. What this means is essentially the graded monad is as close as we can possibly get to these algebras using a graded monad. And this actually kind of gives us some uniqueness of this graded monad. Okay, so then the final thing is we can actually extract some notion of algebraic operation. The algebraic operations are essentially interpretations of terms inside algebras. And it turns out we can extract one such thing for every operation of the presentation. So these are the things that we'd actually use to interpret the effect. Okay, now I'm almost done. I just want to mention one last thing, which is we can say exactly which graded monads actually can be presented in this way. It turns out to be exactly the graded monads that can be presented using the existing notion of graded presentation. So we do generalize this notion, not in the sense that we can present more graded monads, but only in the sense that we can present more algebraic operations. So actually, this is in some sense a nice notion of presentation in that we get kind of a large class of graded monads, but we actually get some nice algebraic operations that we can use to interpret effects, which is somehow the point of what we're trying to do here. And we can also kind of use these presentations to validate some equations. So to validate equations like the things that I showed at the beginning. But that's all I wanted to say. So I'll stop there. Thanks.